Hello and welcome back, guys, to Code a Key. In this video, we're going to discuss another problem, that is GCD of two numbers. Again, very basic problems and going to increase your understanding of mathematics and algorithms. So, what exactly GCD is? Suppose we have to calculate GCD of two numbers m and n. What exactly this means is something like largest number k, such that k divides both the numbers m and k divides n. K divides largest number such that k divides both m and n. Okay, so let us take an example, such as we have GCD of, suppose, m comma n. Okay, sorry, let us say the value of m and n are 8 and 12. So what are the factors of 8, or the divisors of 8? 1, 2, 4, and 8 itself. And what are the factors of or divisors of 12? 1, 2, 3, 4, and 4, 6, and 12. What you can see that these are all the devices, but what we need common, greatest, common, right? Common divisor. We need to find out the common divisor, the greatest common divisor of all. So here, what you can see, 1, yes, it is. So we will make an array where you're going to have 1 as one of the answer. 2, yes, 2 is also there. We need greatest. 3 is not there. 4 is there. 8 is not there. 6 is not there. And 12 is not. So this is the array of common factors. This is the array of common factors. And now we're going to calculate the greatest one. So greatest one is the rightmost one, of course. So the greatest common factor, or sorry, greatest common divisor of 8 and 12 is what? 4. Now let us take one more example where GCD is GCD, we need to calculate of 18 and 25. Here what we will do, we're going to calculate all the factors or divisors of 18, factors and divisors of 25, and what we're going to find out, that we're going to find out that there is no common divisor other than 1. So what you can say, that 1 divides, let me change the color, 1 divides, right? 1 divides every number. So the common factor array or list is going to have at least a number that is 1, because 1 is going to divide every number. So we're going to have at least one common, right? One common divisor. Correct? We're going to have at least one common divisors from m to m and n. Correct? Now let us try to devise an algorithm. What exactly we are doing? Let us try use naive, ekdam, very simple method, very you know unoptimized method. We're going to have number of variables, we're going to have number of time, okay, or space will be more, right? So now what we are doing basically over here is we're calculating divisors of m, we are calculating the divisors of n, and then we are comparing these two arrays and seeing which are common elements, and if the element of this are present in element of this, then what we say that these are the common factors, and the rightmost element over here is our the last element over here, or the greatest element over here is our answer, that is the greatest common divisor. Correct? So what we are doing is, the first step can be like, have factors of, create an array, something like uh, factors of m array. Okay, then we're going to have something like factors of n, sorry. And then what we need to compare, right? We need to see that, like, if I is present in f of m and f of n, if the value, that particular element, is present in both, then we are going to say that this is the cf, the common. We're going to in step 3 or step 4, going to get the common array of common factors, and then we're going to return the largest among all. So the basic, what you can say, algorithm can be like, we're going to have what we're going to have, we're going to have, oh sorry, what we're going to have, we're going to have an array fm, we're going to have an array fn, where we're going to write the factors of m and n respectively. Then for each I, for each element from 1 to n, we're going to, you know, calculate the factors of fn. Okay, if I divides m, then we're going to add it in fn. Similarly fm, similarly if j divides n, then we're going to add it in fn. So this is the calculation of factors. Then we calculate the common factor. So like for f in fn, if f in fm, then we say something like cf dot append, cf dot f append, right? Append f, right? If f is present in both fn and fm, then we're going to append it, and we're going to return the rightmost element of cf. Now let us see the. So this is simple. What we are doing over here is we are just calculating the common factor, sorry, factors of m, factors of n, and then we are checking the common factors, and then we are printing the last number of the array. I don't think I need to, run this, but let us still. Uh, in GCD Naïve, and we need to enter the first number. Let us say 8, and the second is 21. 21. So the GCD is 1. Okay. Now let us try to what? Optimize the solution. So sorry for this. Uh, yes. So what we were doing over here is we were having three loops. Now, can we do it on single scan? Okay, why not on single scan, right? So what we're going to use, we're going to use 1 to maximum of mn, right? Because the number is going to be between the maximum of 2, right? Rather, it's going to be between minimum of m and n, but first of all, let us make that clear that it is going to be between 1 and max of m and n. So what a loop will be like for each I in 1 to max of m comma n, we need to add I to fm. We will be adding I to fm if fm, uh, or that I divides m, right? And is equals to 0. Am I correct? Yes. And similarly we will be adding it to fm if I divides uh, divides n, sorry, if I divides n. Yes, isn't it correct? So why not on single scan? More optimizing, even better. Can we do it on single shot? Here we were doing like this, right? So for each I in 1 to max of n, if I divides m and I both, then we will directly, add it on what? Add it on common factors array, right? It's something like this. We're not going to go to, what? Code and write this code. We're just going to go to the next method, which I'll be explaining you. So GCD common factors array. Okay. Uh, then just uh, here what I need to write is minimum, right? Because the array, the number is on, of course, going to be between 1 to the minimum of m comma n. It's not going to exceed, right? Because that is the common factor. So checking for this, and directly adding it to common factors, and uh, rightmost element. Again, this was, you know better. Now, do we need list? Oh sorry, here's the solution. But do we need list at all? So for that, we only need the largest common factor, right? So one will always be a common factor, right? So each time we find a largest common factor, we discard the previous one. Okay, whatever we found the largest, we discard the previous one. So for that, what we are going to do, we are going to have one more variable, that is mrcf, that is most recent common factor, which will be said as 1. Okay, so for I in range minimum, same thing, but if it is the largest, then what we're going to do, we're going to change it, and we're going to return the most recent common factor, right? And then another optimization, or let us say, where we don't need list, we don't need any extra variable, just an I, that is the loop, like this one. So this largest common factor, if we start from end, right, something like if we want to find common factors between 2 and 4, if we start from 4, okay, this is not a great example. If we start, okay, 8, okay, so if we start from backward, then we will come to know that which is the most recent common factor, right? So start at the end and move backward. So the first common factor that we found will be the GCD. That will be the greatest common divisor, right? And this is the code for it. What we are doing is, as we find the number which is, if like we found that I, just we are returning it. If else, then we will move back to I until we find I is greater than 0, right? If I is equals to 0, then we will halt the program, and that is 1 is the common factor, right? So yes, so this is it for optimized solution. All these three programs that we have discussed right now are having same complexities, they are not different. Okay, how we have optimized? First, what we have done is, we have from start from 1 to minimum was the first optimization. Second was, do we need list to do it? No, we don't. Whatever we find the largest common factor, we discard the previous one and update the value. That is what MCRF, most recent common factor, over here is doing. And then we have scanning backward, and whatever the first common factor that we found, that will be our what common factor, greatest GCD, right? So now, this is not to code off. Let us directly move towards one of the most GCDs, most optimized, I can say. That is not most optimized, but one of the most optimized algorithm. That is Euclid's algorithm. Okay, so I have directly written the algorithm so that it should not mess up. So what we have is, suppose we have to divide both m and n, uh, and m is greater than n. This is the assumption for this. And then what we are going to have? Suppose d is the number which is dividing both m and n, right? So now, of course, we're going to have something like m is equals to a times d, and n will be something b times d. Correct? Is that correct? Yes, it is. Now, so what if we minus these two? We subtract these two, so we're going to have m minus n is ad minus bd, and a minus b times d. Okay, so now what we can say from here is that d divides both m and n as well, isn't it? B divides both m and n as well. So from this we can say that GCD of m and n is GCD of n and m minus n. Now let us code this out, and from that you will be able to understand very better. So this is our code. What we have is, we are first of all assuming that m is greater than n. If it is not the case, then we're going to swap those numbers. Okay, and then we are checking if n divides n. If it does, then we're returning n, and if it does not, then we're going to return the distance m comma n, and then doing the thing that we have discussed. What I have done is just rechecking that m is greater. The first number that is we are inputting is this is a recursive function, right? So it is again it is bigger. That is just to confirm. It is going to be, but still, just to confirm, I have just written the max and min function so that the first number should be bigger and the second number must be smaller. Was that correct? Yes, it was. But this particular algorithm is not that efficient. Okay, let us consider let us consider a case, or let us first of all discuss this one, because this is the same. The second algorithm that I have written is also the same thing. There is just a slight difference. Here I'm using while loop. That is, we can say that the first method, that is this one, is iterative, and this is recursive. So what we're doing over here is, again swapping, assuming that m is greater than n. And then at this point what we're doing is, we found if we found that n divides m with remainder 0, and then we are done, we are returning n. But if it does not, then if it does not, we we do the same thing, like difference, taking out the difference and then returning n after that. Okay, so What is the problem with this method is, let us consider that we have to calculate GCD of 101 and 2. Okay, 101 and 2. So what it will do is it will subtract it, right? 99 and 2, then something like 97 and 2. It will go on and go on until we found something like 5 comma 2, right? GCD of 3 comma 2, and now at this point it will be smaller. At the time it will be smaller, and then we're going to get 1. you know isn't it much lengthier than before? It is worse than previous one. So what we're going to do is we are going to do something even better. We're going to suppose again the same thing. uh, this is again the Euclid algorithm only. Okay, now we're going to here suppose that n does not divides n. Okay, like in the previous case, that n does not divides n. Then what we're going to have is m will be q times q times n plus r, right? Q times n plus r, where q is the coefficient, r is the remainder, and m divides n. That this is what we have studied in lower classes. Assume D divides Mn, and again the same thing, and we are doing this, and we are putting the value M in place of M. We are substituting AD. In place of N, we are doing BD, and this is R. So it will follows that R is CD, and D also divides R as well. Okay. Now, if we try this, and this is the exact algorithm, we are going to consider that. Sorry for this. We're going to consider that GCD of a number. Okay, wait. We're going to consider GCD of m and n, where we're going to assume this. We're going to do if m divides n, then we're going to return. Otherwise, we're going to do this. Remainder is equals to r uh, m modulo n, and then we're going to return the n comma r n comma r GCD. Now let us try this out. You can try this out. Like you can get the GitHub link below, and you can run the code, because all are same, right? We're calling GCD, right? So what we have over here is we are swapping the numbers. Because we are assuming if we found that n divides m, we're going to return n, and then we are doing this thing that we have discussed over here, right, in the presentation, right? So now let us run this. Now let us again enter the first number. Something, oops, what happened? 101 and 2. So we're going to get option none. Why? Oh, sorry. We're going to return GCD of what? GCD of n comma m n, right? N modulo n. Now let us run that again. So what we have is 101 and 2. So we got 1. So this is it for this video. I hope you like it. Make sure to subscribe, like, and share to your friends. You can check out the previous video. That was, I guess, factorial. And the next video we'll see what it is. Okay. Thank you for having me.